Hey everybody, I want to go over the homeworks from the second part that I assigned, and the first one I want to go over is number 27. And so 27 is the so-called ternary search algorithm, and it asks you to write down the algorithm in pseudocode. It's not made very explicit there, but I really wanted to see some pseudocode. I hope if you have not done that, perhaps stop now and go and do it and see that you can do that, because you have to practice this writing pseudocode, because there will be a question where I'll ask you to do that. Okay, so repeat if you have done your homeworks, but somehow you interpreted it differently, the question. You didn't actually write down the pseudocode, so do that first before you look at the solution. Okay, so what's the ternary algorithm? The search algorithm does, it's very much the same. So we have this list here, we have a beginning and an end. I'm going to use a little bit the notation that I have and the ideas from the lecture where I discussed this. I'm going to write back instead of beginning, because it's so too long otherwise. But instead of, in the binder search, we would cut it in half, right? So we're going to cut it in 3 equal, or almost equal parts. So I'm going to do there and there. Okay, it's not almost equal. So, okay, that's a good thing is then, well, we have to find exactly the positions. And what we did in the binder search, we took the last element of the first group and compared our x with that element. But now we're going to do two comparisons, right? We have to determine whether we're in part 1, part 2, or part 3, right? So we have now list 1, list 2, and list 3. Three lists, and which of the lists are we in? So I'm going to use this element. You could have chosen this element. It's all a little bit, doesn't matter really how you do it. In fact, I'm not 100% sure that if my implementation, I have to find an element that's one of these two elements I'm just decided to take this one. I don't know why. And so what I'm going to do is I'm going to compare x with this element. Is x, what is it? We have to think about it, right? So we would write is this element here. Are we less than x? Sorry, let me write it this way. So here the question is this less than x? And here the question will be, is this bigger than x? No, that's that's saying the same thing, right? Sorry. I think, I'm not 100% sure, but I think it's better to do it this way. If are we bigger than x? Okay. So if we're less than x, then we know that x must be in group 2 or 3, right? If this holds, then we know we're either in 2 or 3. If this holds, we know we are in 1 and 2. And therefore, if we do both comparisons, we know exactly where we are. Okay? Because, okay, right, I hope this is clear, right? So that's the idea. Now, that means I have to, instead of halfway, I have to find the location of these two elements. I'm going to give them names. I'm going to call them the first one and the second one, F and S. Well, I don't know. I'm just calling that. So let's think about how to implement. So our procedure is called ternary search. So let's call it turn search. And again, we get a list of elements, ordered list, of course, A1 less than A2, ordered like that, and elements. Okay, so let's think. What we want to do? Well, first of all, we want to, the way that we're going to keep track in which list that we still have to look for is by changing the beginning and end point. Right? So if, for instance, if in the first check it became clear that I have to be in the second interval, I have to make the beginning now here and the end should be there. Okay? If, on the other hand, I know I'm in the first list, the beginning stays the same, but the end becomes this. Okay, so it's just, instead of looking at two possibilities, there's basically 3 possibilities each time. So, therefore, I need to keep track of beginning and end. So beginning originally is 1 and end originally is n. So we just make sure that we start well off. And then, and then the next thing, what we do is, well, remember, when are we going to stop? Let's stop at exactly as we did before. We're going to stop if we are left with a list of just one element. which means that beginning and end are the same, right? So the way that I make this keep going is until I cut it down so much that there's only one left. So while the beginning is less than end, I will keep going. But once they are equal, then I know that I just have to compare with the one element that is left, I compare it. That's where the actual comparison with x goes. Okay. Well, not true, but I mean that's where we figure out whether x is in there or not. All right. So what do we do? We need s. This f and s now. The two positions. So I'm going to declare f. Let's think about what this should be. Well, it should be the same, right? It's now not the midway or the halfway point, so not the average, but you take the sum of the both and divide by 3. Does that make sense? Let's think about it. Okay, if I have a list, say, from 1 to 15, then this would be 5 elements here, so this would be the 5th element. There would be 5 elements here, 5 elements here, so this would be the 10th element. So this would be 5, 10, this would be an 11th element. So what am I calculating here? If I do beginning plus end, 1 plus 15, that's 16, divided by 3, and rounded down, that is 5, okay? So I want to see now, how do I get this? I could do here, for instance, the end point, the second point, it really doesn't matter. I think, I don't know, you could do twice f. But that put me here. So you could do twice f plus 1, for instance. So I'm going to do that one. 2 times f plus 1. Right, that puts me exactly twice f would be the end point of the second one, but I want the beginning point of the third one, so that's why I'm adding 1. Remember, f and s are locations, right? F and s are the locations of the two testing points that I'm going to use. This end point of the first group and the beginning point of the third group. These F and S are the locations. So if you want to add that, remember, you can put this here, right? So F is a location at the end of part 1. S is a location at the beginning of part 3. Remember, in comments you can write whatever you want, right? But make them just separate them with these braces here. Okay, so that's F and S, and what I need to do, well, now I have to compare X with these guys, right? According to these two principles here. So there's an even then and twice even then. So if then, so let's see what we want to do. I want to compare if AF is less than X, this is this comparison. Okay, so let's think about what can happen here. If this is true, then I need to do another search, right? Because if this is true, then either I'm part 2 or part 3. So I should then do the second check. So if then, so now I'm going to compare with the check is AS. Remember, AS is supposed to be this element. Is this bigger than X? Okay, so let's think. If this is true, what does this mean? That means that by virtue of being here, I know already I'm in part 2 or 3. This tells me you're actually in part 2. So then I'm in part 2. What does that mean? If I'm part 2, that means that the beginning of the list is now F plus 1. Remember, this is F, so it's F plus 1. Okay. Else, if I'm not in the beginning of the list, sorry, if this is not true, what does that mean? That means that I'm actually in the third part of the list. So that means that sorry. I changed the beginning, but I also have to change the end. I forgot to do that. Sorry. So if then, so let me do this a little bit more, since there are several operations here. Let me put it this. So this, oh, that's the wrong type font. So if this is true, so what do I do then? Then the beginning becomes now this element, an element just after my first element. So the index of the beginning is now f plus 1. But the endpoint also changes, but the endpoint is now becoming this guy here, which is one less. So that is g minus 1, right? I'm just recording what it is. That's if this is true. If it's not true, so else, what does that mean? That means I am in the third part. In other words, I only have to change the beginning. So then beginning, and to what should I change it? Well, I should change it to this position, which was position S. Notice that it is S now, not S plus 1. That the beginning is S. This all was when the first test was positive, which meant that I'm in a second or third part. Okay, but if this test is not true, then I do something else. That's the else here. So this else, remember, look at the way that they're aligned, right? So let me kind of perhaps I use the alignments here. So this is a line that means this if is carried out, whatever is indented here, so this indentation, this whole part will be carried out as long as I am will be carried out first, and then I jump to the else. Okay, sorry, there's a lot of things that makes it now illegible. Okay, so else, what do we have to do? Remember, if this is not true, x is in the first part. I don't change the beginning, but I change the endpoint, and the endpoint should now be this guy, which is just f. Okay. Else end is f. Great. Now don't forget that we have to end this. Well, this is while loop. And while this is happening, we still have a list of a certain size. But when this while loop ends, beginning and end are the same. We have one single element, and then we carry out the actual test one more time. So if x is equal to a end or a beginning, because they are the same, and the beginning are now the same index, so we're talking about one and the same element. If this is true, then record that location. So then the location is exactly the index, and else the only thing that if this is what can happen now means that x is not there, so location should be 0. And then finally return location. Okay, so I hope that's sorry, this was supposed to be at the same size. It got a little bit, it's not supposed to be indented here, because this is of course important, right? And this you almost need checkered paper or something like that to make sure that, because if this is interpreted as being indented, then this would be carried out within that while loop, right? And we don't want that. We only want to carry this out after the while loop has ended. Okay, good. And then the next question was number 42, and that was another kind of insertion, another sorting thing. It was called the selection sort. And what it basically does, and it's perhaps the most naive way that you would think of doing this, is you say, okay, I have to sort a list. I'm going to find the smallest element, I'm going to put that first. And then I take that element out, and I'm going to do it all over again. So each time I'm looking for the smallest element in the list, and whatever list that is remains, and I'm going to put that next. Okay, so for instance, if I have to sort 4 through 7, 1, and 2, say, what I'm doing is I find the minimal element in this list. That would be 1. So I put 1 first, and then these things I don't know yet. So I'll put question marks here, and then I scratch out 1. So the next step would now be, I'll do it in different color. I have 4, 3, 7, 2. So what is the minimum of this new list? 1 is no longer there, that is 2. So I have now 1 and 2, but again, I don't know what's going to come here. I scrap out 2, and I look for the minimum. I find the next step would be 3, put it there, 4, put there, 7, put there, and that's it. Okay? So let's write down a pseudocode, and I'm going to cheat a little bit. So on purpose a little bit. So I'm going to call this procedure selection sort. So cell sort. And again, we get a list, A1, A2, A3, and of course, unordered list, otherwise we don't need to do anything. There are now many ways of doing it, and I want to show you a different way, something that is often also used in computer science. So we have this list L here. When we described the bubble sort, and in pseudocode, we haven't done, today you saw also the description of the other sort, the insertion sort. You see that what we do is, what was I saying? I lost my train of thought now. That we reordered the original list. Okay, so at the end, A1 was the smallest, A2 was the second smallest, and so on, etc. But it's sometimes better to make a new list and call this S. Okay, so what I'm going to do is, or B's, I'm going to call B's. So what I'm going to do is I'm going to call B1. So if I did this, I call B1 1. That was the first element in my list. Then I found the second minimum element was 2, so I'm going to go B2 equals 2. So I'm going to create a new list, the BI's, where the first element will be the minimum of the original list, the second element will be the minimum of the list remaining after I removed the smallest element, etc. Okay? So let's build this. So what we have to do? Well, we have to construct this. I don't know how many B's we're going to have. Well, exactly how many as there were A's, right? Because the B's are the A's just renumbered. Okay, so this means I go a loop for, let me think whether I have to initialize something. So for 2, perhaps I need to write something in there, I'll figure that out later. For I going from 1 to n. I'm going to define my BI. Okay. Okay, so here's where I'm going to cheat a little bit. I can decide how I represent the input. And so I'm going to say my input will be this. My input is a list L, and the list consists of the number A1, A2, all the way up to N. So I have this name for the list L as well. Okay. And so what I now do is the following. Look at what I'm doing. I'm going to take the minimum element. So at each stage, if I is 1, then I'm doing this. If I is 2, we are doing this. Okay? So, but look also what I did here. I changed my list L each time by deleting something. So I'm gonna at the one hand define my BI's as the minimal element of the list that I have currently left. Okay. And that is originally when we start, it's L, but as we progress, we will throw elements away from L, and we will call that the new L. Okay? So, what I will do, I call BI is the minimum of the list, min of L. Now you will say, hey, whoa, Professor, don't you have to implement that? Yes, I kind of should, but I kind of also assume that it is a procedure that I already know. After all, if you look at the example, the very first example that we did in the textbook, that was or in the lecture, was finding the maximal element. Well, okay, finding the minimal element is similar. So in other words, you use the procedure that was called max there. Well, you adjust it and make it the procedure min, and you call it. So I'm now saying, okay, the cell sort, the algorithm I'm describing is a much more complicated thing, and I'm using smaller algorithms that I know can be made. And that's why I'm saying I'm cheating a little bit, because I'm not implementing actually how do you find the minimum. But if you want to see, look at the, it's a good little test to see whether you understand everything. I think it was even a homework problem in the first lecture on this topic, to write down an algorithm for that. Okay. But I need to do something else. Remember, once I have declared BI is the minimum of L, I should now redefine my list by taking away that minimal element. Oh, BI, let's call it BI, it's BI, right? At this point it is the same as BI and it's just less writing. So this is the part where I scratched out the element. So now I have a list with one less element. Now again, you might say, yeah, okay, professor, but it is perhaps, it sounds very simple, but do we, oh yeah, right, sorry, apologize. I always use this minus and in the textbook uses this minus, right? What I mean is, so if you want, throw out BI from L, or delete perhaps that's better. Delete BI from list L. And perhaps it's a comment, let's write it like that. True, it's something that you need to implement that, because after all, it means that we have to rename some of the A's here. Right? So I agree, it in itself is something that needs to be implemented, but again, we can think of it as an algorithm that we have already set up. Namely, we have a list and an element in that list, and we make a new list by throwing out the element. That should not be hard, right? And you can imagine to write down something. There's no example in the textbook, so perhaps you should try yourself. Okay. So, let's think about this. I think I'm done, right? Because what is happening here? I define the next best element. Let's look at the two steps I do. Here I take, at whatever list I have, I take the smallest element of it. And that's my next element, because remember, I'm going from 1 to n. So I have already, at stage I have already B1, B2, B3, up to BI minus 1. I have the previous ones. They are supposed to be already in order. So this will be the next one, because this is the smallest element left, right? So, okay, so this is doing what I want. It's going to find the next smallest element, and it puts it in the right position. And moreover, it throws it out of the list so that I don't take it next time anymore and repeat the process. Okay, and so what you will get is an ordered list. As a bonus, by the way, if these elements are all distinct, it works, but even if some of them are equal, it still works. Right? You will have, of course, you have a list with repetition, but that can still be ordered, right? The list 1, 1, 1, 5, 7, 9 is an ordered list. Not strictly ordered, but it is ordered. But that doesn't really matter. So I'm kind of done. And the BIs, so return B1, B2, all the way up to Bn, and that will be an ordered list. Okay, and if you're not 100% convinced, we should run this through here. So let's run it for just 2 steps. So okay. Repeating what I did. So what was this is the original list. What is the list after this process? Well, the list is now 4, 3, 7, and 2, right? Because I took 1 away. And if I now look at this list, the smallest element, so here was I was 1, now we are I equals 2, as we loop through this loop. I'm defining B2 to be the minimum. So, okay, this 2 is this minimum, right? Okay, I hope that the 2 and the 2 is not... Okay, let me do it on the list. I want to just do it one more time to convince you that I'm right. Let's list 10, 8, 14, 6, and 7. Okay, so I is 1. This is my L. When I is 1, I calculate B1 to be the minimum of this list. And what is the minimum of this list? Well, that is clearly 6. Well, I have implemented something that, and how did I implement it? I just start looking for the smallest element. I said the smallest element at the beginning is, I don't know, 0, but then if I progress, it becomes, well, I shouldn't say 0. Okay, that's a little annoying thing with the minimum is where to start. I'm not going to address this. Okay, so B1 is 6, and then I make a new list, namely, this step I've carried out. Now this step is now that the list is throw out 6, so 10, 8, 14, and 7. Okay, so now I is 2, therefore I'm defining B2 to be the minimum of my list. But what is the list? This is now the list, so the minimum is 7. So, and the new list becomes 10, 8, and 14. I threw 7 out. Then let's do one more step. I is 3. B3 is now the minimum of the list that remains, which is 8. And the new list becomes 10 and 14. And I keep doing this. I mean, okay, now since I'm almost done, let's quickly do it, right? So I is 4. B4 is now the minimum of whatever list is remaining, that is 10. And what is my new list? L is 14, and of course, when there's only one element, I know already what the minimum is. It's going to be 14. And as you see, the B1, B2, B4, B5 is 6, 7, 8, 10, 14. So the output of this thing is exactly 6, 7, 8, 10, 14, as I wanted to do. All right, that was it.